So the question was, why do aluminum pots corrode and things like that? Turns out, even since the 1930s, we've made aluminum-clad composites called alclad. Okay, alclad composites have a very thin layer, about a human hair thick, okay, 2 to 4,000 thick, of pure aluminum on the surface. And the pure aluminum has excellent corrosion resistance, excellent pitting resistance. So if I have an aluminum 4 copper alloy, this is a piece of something called Novellus fusion. Novellus is the sheet metal spin-off of Alcan. When Alcan merged with Pechenay in France, which was the Alcoa of France, okay? There were 2 guys who invented a process in 1888, and actually last spring in my class, one of the people did his presentation was on Hall, Charles Martin Hall, who was the founder of Alcoa, and Perot, Perot was Hérault, H-E-R-A-U-L-T, Paul Hérault invented the exact same process within 2 months of each other, you know, thousands of miles apart, no communications between them, of refining aluminum and making it cheap. Before that, aluminum was more expensive than gold. The crown jewels of the French royal family were made out of aluminum rather than gold. And they had aluminum dinnerware because it was so light and unique and it was more valuable than gold. The top of the Washington Monument, they have a little 4-inch pyramid on top of the Washington Monument for a lightning rod. It's aluminum because at the time it was more valuable than gold in 1880 something or early 80s. It wasn't until 1888 that Hall and Hérault developed this process. The aluminum, pure aluminum is very soft. I mean, it's soft, it has the strength of plastic, okay? 6 or 7 KSI strength. 1 megapascal, if you want to put it in megapascal terms. Well, what they did is they would roll bond. They'd roll out a 2-inch thick pure aluminum, and they'd take a 20-inch or 30-inch aluminum alloy casting, and they roll bond them together in the rolling mill. And I just read something recently at a 15% success rate. Okay, wasn't a very good yield. But Novellus fusion came along, and it turns out they can co-cast pure aluminum with the alloy, and the alloy has lousy corrosion resistance but high strength. And so you roll this in sheet metal, and you end up with like 2/1000ths of pure aluminum on the surface, gives you excellent corrosion resistance. The outside skin of all Boeing aircraft, Airbus aircraft, it's all alclad. High strength alloy in the center, okay, that's the peanut butter and the peanut butter sandwich. The bread is pure aluminum, excellent corrosion resistance. So it's a composite. And this process has essentially 100% yield, okay, because it's bonded in the casting operation. So it's sort of a development. The brought into the market about 10 years, plus 10 years ago, okay. Anyway, so these are the non-heat treatable aluminum alloys, some of them, and let's blow these up a little bit. 1100 is 99% aluminum. That's sort of architectural and decorative applications, furniture, deep drawing, parts, hollowware. I mean, things don't have to have much strength. Bottom of pots and pans for the kitchen. Okay. 1060 is 99.6% aluminum. So you can see 1% impurities, 0.6% impurities, and actually have other alloys in between that basically follow that pattern. 1350 is 99.5% aluminum, electrical conductor. So you see these 350,000 volt transmission towers, and you see the cable strung in between. It's aluminum. But guess what? It's got a steel core for strength. Okay? Aluminum for electrical conductivity, not thermal conductivity. Is electrical and thermal conductivity with metals go together. There's actually a formula from 100 years ago that equates the two. They're not absolutely equated, but in 100-year ago terms, they are so correlated that there's actually a formula relating electrical conductivity and thermal conductivity. And it is related to reflectivity of the metal. It's related to the free electron concentration. Better electrical conductivity, you're going to have good thermal conductivity in virtually anything, okay, that's metallic, with metallic bonding. Anyway, we could go into that, but I'm not going to go through that. Then we get to the 3000 alloys, and it's just got 1% manganese, okay? May have some other little things. This one's got a little bit of magnesium for extra strength. Sheet metal requiring higher strength. General purpose applications where high strength and formability are required. Process and food handling equipment. Okay, well, it's soda cans, folks, mostly. Electrical conductor and architectural applications, 5005. Here are the kind of alloys. This is structural application in tanks. 5456 actually says, should say marine components, okay? These are 20 KSI, 25 KSI strength levels, not tremendous strength, not as strong as steel, but a lot lighter than steel, okay? So if you need to move something, this is what you're gonna do. And you can weld them to full strength without any great difficulty. We'll talk about some of the welding problems later. So here's heat treater's guide for aluminum alloys, and we have these 2000 series alloys, aluminum copper with a little magnesium or silicon, and you get precipitation hardening. Aluminum copper lithium alloys. Here's an 8000 series extruded bar. Okay. Lithium actually has an interesting property in that it's lightweight and it reduces the density of aluminum by 10%. It also increases the Young's modulus of the material by 10%. And E over rho is the important parameter for structural stiffness. So if I want to have something that's slender and stiff, I want a good E over rho, and lithium alloys can give me 20% more than typical aluminum alloys. So they started making part of the space shuttle main tank out of aluminum lithium alloys at the end of the lifetime of the space shuttle. A lot of the 787 aluminum components, Boeing 787, are 8000 series aluminum lithium alloys. Okay. The Soviets first discovered this stuff in the 1970s, and we worked on it for 30 years. Alcoa worked on it for 30 years. And finally, after 30 years of development, there's lots of problems with hot cracking and during welding and other things, but Alcoa, after 30 years, finally solved one of them. Okay. They're still somewhat of a pain in the neck, and they're still pricey because aluminum is very reactive, like titanium. So how you cast it, melt it, and mold it is a little bit different. But we're now using aluminum with lithium alloys. The odds of using it in a corrosion critical application like a marine environment, okay, it's not that weldable, okay. It is a heat treated alloy, and the lithium actually makes the corrosion worse. But when you're maintaining an aircraft that's worth $200 million and you've got mechanics on it, not like helicopters, 2 hours of maintenance for every hour of flight, but a commercial aircraft probably is at least 1 hour of maintenance for every hour of flight, okay? So that's per person hour, right, of flight. Helicopters are the worst. So aren't you glad you don't work for NavAir? NavSea's, well, actually NavSea's got plenty of corrosion problems. Okay, in fact, I always say the Navy is the corrosion leader in the services. They're surrounded by salt water. So here's that type of phase diagram, and they're making, this is copper, aluminum copper, and you have to solutionize by bringing the stuff up while it's still solid in this range, and then you quench it down to low temperature, and then you can precipitation heat treat in this range. If you're going to anneal it, you use these ranges of temperatures. This is 400 centigrade, 200 centigrade, 500 or 400 Fahrenheit here. okay? So it involves a heat treatment process, which looks like, here's this, so this is the heat treatable aluminum alloys that are not as weldable. We can weld them, but we just can't get full strength because we don't have the heat treatment. So you go up to the solid solution, punch it down, and then your heat treatment process cycle with time looks like this. Heat it up to 940 F, hold it for an hour for an inch of thickness, quench it in cold water, heat it up again for 10 hours at 340 degrees and cool it down, and you'll double or even triple the strength. Okay? Here are the tempering curves. If you want to know how long it takes to harden something and then soften it. Okay, so far as that goes. So here's your hardness number, Vickers pyramid hardness. We talked about hardness testing. So it's an easy way to test what we're doing. The as quenched hardness is way down here at solid solution, and this is a annealed product. Okay, it's dead soft. And if you just leave it at room temperature, after an hour it starts to harden just naturally as the precipitation takes place even at room temperature. After 10 hours you actually reach a significant increase in strength, and that will go out till hundreds of thousands of hours, which is 10 years, okay, or 20 years. But if you heat it up a little bit, this is at 230 degrees Fahrenheit, you can actually get, depending how long you hold it there, 100 hours or 10 hours. Let's take 10 hours. If I want to do a 10-hour heat treatment, at 329 degrees Fahrenheit, I can go up and I can double the strength to 110 Vickers, and that's where we call that's what we call one of the heat treatments to optimize strength. But we have problems with optimized strength, and I'll talk about that in a second. Okay, but there's a whole series here. If you heat at too high a temperature, you reach the peak and soften before you get the optimum. You don't usually want to wait 100 hours to get the maximum strength, where you can get 2.5 times the strength, but you can. They once did a study. The Wright brothers engine is at the Smithsonian, and someone took a little sample off, put it in the scanning electron microscope, and they looked at how the precipitates of the aluminum copper precipitates had grown over 100 years, or actually 90 years from the time they did it. And they could plot on a graph, you know, a log type scale, and those things are still coarsening at room temperature, sitting in the Smithsonian, right? You know, everything falls on a straight line. Okay, they're getting coarser and coarser over time. Okay. There's a number of different designations. So let's say I have 66. Well, let's do 7075. So 7075 is an aluminum, magnesium silicon heat treatable alloy, and it might have a T-T6 designation. This is the alloy composition. Okay, it's defined in the tables. T6 means it's heat treated. Okay, so they have, the aluminum alloys will typically have a dash designation. Dash F means as fabricated. Dash O means annealed. Okay, wrought products only. So I got 5454 aluminum plate, not heat treatable. I might get it in the annealed condition. It's as soft as it gets, but it's still got reasonable strength. H is cold worked. Let's say I get it in the annealed condition and it's 2 inches thick, and I put it through the mill and I go down to 1 inch thick. It's now harder to do the cold work.
This is compression.
Just compression, okay? The grains have gotten smaller. They turned into pancakes from what we call equiax. They can become planer type grains, and you get greater strength. So what you're going to build the hull out of is going to be an H something, okay? H2 is quarter hard, 4 is half hard, 6 is 3/4 hard, 8 is hard, and 9 is extra hard. It's just how much reduction did I have, how much cold work did I put in it. I can more than double the O value with H8 or H6 maybe, okay? So I can go from an annealed, which might be 10 KSI, and I can get up to 20 KSI, or I might even get up to 25 KSI in some cases. There's solution heat treated, where a heated it up, quenched it down, but I haven't done the tempering, because I'm gonna do that later after I do some forming and other things. Because once I've heat treated it, made it hard, it's difficult to do the forming. Heat treated in a stable condition, which means it's not gonna keep on precipitating, and there's lots of different versions of this, okay? Depending on the aluminum alloy, there's different ways you do it. T6 is solution heat treated and artificially aged to the optimum condition, okay? Well, it turns out the optimum condition doesn't have the best stress corrosion cracking resistance. And here is an example. I got this from a guy who graduated in mechanical engineering at MIT, had a PhD, and he was working for a company called NavTech. Okay, and NavTech used to be here in Massachusetts, but it moved to Connecticut. But they make specialty marine hardware for fancy yachts and America's Cup boats and things like that. Okay, so pretty expensive stuff. This is a hydraulic cylinder which operated, part of a hydraulic cylinder that fractured, that operated at, so this is 2002, Steve came to me, here's the letter from him. It was 7075 T6 alloy, okay, that they were using, which had a so the 7075 T6, which they had been using, had a yield strength of 73 KSI, really high strength aluminum, had a toughness of 26 KSI square root of an inch, and had a wall thickness of 1/8 of an inch. And it operated at a pressure of 7,500 PSI. So 1/8 inch wall, a little over a 1 inch diameter tube, 7,500 PSI. Would you like to stand next to that if it let go with hydraulic oil? Well, neither did the guys working the winches for the sails on the American stuff. And this one did let go, and they were concerned about this. And the problem was it was stress corrosion cracking, which aluminum alloys tend to do in saltwater environments. American cups tend to operate in saltwater environments. Let me see if I can still see. I don't know if I can still see this is 12 years old now, and it oxidizes over time. So. Yeah, right there. Okay, it's not the clearest. Here's the stress corrosion crack. I agree, it's not the easiest thing to see, but you guys, make it up if you can.
That's good.
Where's my pointer?
Yeah, is it the lanyard?
Yeah, the one with the lanyard? So, over here, okay. Thanks, that's why I keep the lanyard on there, okay? I have others, this one I like. Let's see if I can focus that a little bit. I'm supposed to have automatic focus. Oh, well, okay. Right in here, there's a thumbnail crack. You kind of see, can you imagine that? It was clearer before, okay, 12 years ago. But if you look at the texture here, I guess I could blow it up some more. There actually was a color differentiation when I looked at it 12 years ago, when they brought it by my house one Saturday morning. You see a little texture? There's a little, what we call a thumbnail crack right there, and there's certain lines radiating from there, okay? Maybe you have to look at these things for 30 years, but I see it, okay? And I agree, I mean, if you haven't looked at these for a number of years, it may not be as obvious, but right in that area, that's the fracture initiation. It went about 1/3 of the way through the wall. Okay, it went about 1 millimeter deep before it fractured all the way through. And I'm sort of looking from experience at some of these other features on here. You see lines radiating, these are coming out at an angle, straight down lines. You can kind of see those lines, right? Okay. So maybe I kind of integrate things with my experience, but I can see the crack. And it was more visible at the time. But, I mean, you can, and I've played with it since then, and it's not as easy to see now as it was then. Or maybe I'm just getting old, but if you want to look at it, you can pass it around. So that took 7,500 PSI. It turns out, Steve explained to me, in the America's Cup business, if something doesn't fail after 100 hours or 200 hours, you made it too heavy. Okay? They're going for lightweight. I mean, this is a $100 million rich man's, you know, venture or pride or whatever you want to call it, to tell some other billionaire, I beat you at the America's Cup, right? And so you'll go and hire some MIT professor in marine engineering doing ship design to design your hull.
All those pictures up in that room we did our orientation in, like all those different, like, years back, they won the cup, teams.
They won the cup, and actually one time they had Jerry Milgram was one of the designers, and the other, I can't remember the other professor, they were on two different sides. And then 3 years later, they combined into one side to beat some other country, the Australians. I don't know who was winning back then. I mean, it had sort of an active competition in the department, okay, among the faculty of who could do the best ship design. You guys have to do a ship design your third year, right? Or the second summer or whatever. Well, these guys had to do a ship design only. They were being paid pretty well for it.
Yeah.
Okay? Better than you, okay? Maybe not better than all, well, probably better than all of you put together. Okay. But nonetheless, okay, we don't have to go there. Okay. So, anyway, if they don't fail fairly often, they're too heavy. You should make them thinner, okay? And weaker. But you want them to fail safe, not to fail unsafe. And obviously, breaking in two like that, you could damage, you could kill somebody, okay? So they want them to leak before they break. I talked about leak before break before, okay? So Steve came to me with that and says, what do we do? What do we do? And I said, well, you got a T6 heat treatment, and T6, it's well known, is very susceptible to stress corrosion cracking. If on those annealing curves that I showed you, we went and overaged just past the peak, okay? If we were on this curve right here and we went just past the peak to right here, we could sacrifice a little strength and get a lot more toughness proportionally, okay? And that's called a 7075 T73 heat treatment. T7 heat treatment means slightly overaged. T6 means optimal aging, maximum strength. T7 is optimal aging for high strength and corrosion resistance. And the properties, we go look it up in the handbook, the properties 63 KSI and 30 KSI root inch, that's square root inch. And it turns out, in my calculation, to make everything work out in terms of strength, we had to up the wall size to be able to hold 7,500 PSI, right, operating pressure. So it turns out, I ought to write this out someday. It was operating at 63% of yield, was their design criteria. And you have the fracture toughness is equal to sigma times the square root of pi c, which is the crack length. And we want the crack length to be greater than the wall thickness, so it'll leak before it breaks. And so K is 26 for the T6. Sigma is, turns out this is 46 KSI for the T6 condition, equals, turns out there's a 1.12 multiplier out here that I've told you guys about. times square root of pi, oops. Yeah, times square root of pi c. If you solve that, you find the critical crack length is 0.08 inches, which is 2 millimeters. I told you the critical flaw size that we saw on the piece was 1 millimeter. What I didn't tell you, this is the half crack length, okay, for a crack at the surface. Internally embedded crack would be a 2C crack, but on the surface is a mirror plane. So when you do the fracture mechanics, it's the half crack length. So there it was. We proved the critical flaw size was 1 millimeter. We looked at the sample, and I could see it was 1 millimeter deep before it did a brittle fracture, okay? So that explained why you had a brittle fracture, and the whole thing split in two. So then you go to, when you do, we ended up working out on my dining room table, 59% of 63 KSI. We just kind of probably could have done this in a computer, but it's 37 KSI. And we just said, let's make it 140. And so now you got 30, which is the fracture toughness. So, you know, it's supposed to be a 31. 30 over 37 equals 1.12 square root of pi c. If you work all that, c is equal to 1.166 inches, which is greater than 0.140 inches. They should have a leak before break. If you just change over heat treat to get better corrosion resistance, better toughness, but lose yield strength, increase the wall a little bit. Hey, we're adding weight, sorry, if you want to be fail-safe, sometimes you have to trade off, right? But there it is, I can have leak before break. So I solved the problem, or we solved the problem together, and I told him my consulting fee was, I want the part to show the class. Well, I took about an hour, okay, to look things up and stuff. But it shows you how, you know, this is an example of how you can work out a problem. They were going for lightweight, maximum strength. They had thought about fracture toughness or leak before break. But when they had a failure and it was an unsafe mode, you go back and re-engineer it, and you end up with a solution that says, oh, I can solve this. Okay? In this case, it was a successful change in design. Okay? Okay, we'll see you tomorrow. We'll finish up a little and start the mechanic. And we got one. Who's tomorrow?
Is it?
Oh, I thought we had one today. I thought you told me 5 this week. That's okay. That's fine. I can talk.
Everyone is complete.